Please use these notes to update your class notes. There are three common ways to determine free energy for a system. Remember, free energy is referring to the standard Gibbs free energy. If we take a look at the symbol for standard Gibbs free energy, we have change in Gibbs free energy, the standard symbol referring to at standard pressure and temperature. The change in free energy that will occur if the reactants in their standard states are converted to the products in their states. So, for example, we have a chemical reaction with reactants nitrogen and hydrogen being converted into ammonia. The free energy associated with that is negative 33.3 kilojoules. From this number, you can deduce that this is a spontaneous reaction. Remember, delta G values that are negative imply that the reaction will occur without any prompting. This value is often reported in kilojoules. That's the most common unit. And for some reason, it's not written kilojoules per mole, but it is. It's always kilojoules per mole. So when you see this value, you kind of need to know that it's the free energy that's associated with this respective number of moles, the 1 and the 3 moles of reactants, the 1 and the 3, and the 2 moles of product as shown. If for some reason a coefficient was multiplied by that, then a coefficient would need to be multiplied by the free energy as well. We can calculate Gibbs free energy in a variety of ways. One of them, we have used this equation in class before, and some things you want to remember about this equation is that enthalpy will be reported in kilojoules per mole. Temperature should be in kelvins, and entropy will often be reported in joules per Kelvin mole. So it will be important to remember when using this equation that joules will need to be converted into kilojoules, or you could convert kilojoules into joules, but these two units must match. Of course, you can see kelvins will cancel, moles will remain, but again, it's often not going to be written in a textbook or a worksheet. That is just the standard way. So here's one way that we can then calculate Gibbs free energy. A second way is to use the equation that we tried last night for homework. We can use the standard values for free energy from the appendix. Those would be given in a table on a test or quiz. And then finally, we can use a method similar to how we worked with enthalpy, where we combine the free energies using Hess's law. Because free energy is a non-state function, meaning you can arrive at it either in one step or in many steps, if we have a series of elementary steps, like is shown here, that sum together to an overall reaction, then the individual free energy values for the elementary steps can be combined to arrive at the overall value. There are a few things to remember when we use this method. One thing is that a reaction can be flipped. That means put the reactants and products on the opposite side of one another. And if that is the case, then we need to change the sign on the delta G value. Right? If it's positive, we make it negative. Negative, we make it positive. Another thing that we need to remember using this method, G may be multiplied by some coefficient, which I'm just going to call x. And if that is the case, then that means the delta G value should be multiplied by that coefficient x. So those are the most common skills we will use when combining elementary steps to come to an overall delta G value. If we examine the example that's given here, we can see that the first reaction has been reversed, and so a negative symbol has been put in front. The second reaction has been multiplied by a 2, and so a 2 has been multiplied by the delta G value. This must be the overall reaction, and the way that we would know that is we would be told, right? We would typically, in this type of problem, be given the overall reaction, asked to rearrange the elementary steps so that they can sum to that overall reaction. And once we do that, then that means the delta G values will also sum to the appropriate value that represents that overall reaction. Some of my notes on the side is that while it's true we could use delta S of the universe to calculate or predict whether a reaction is spontaneous, it's more common that we would use delta G. Just as a reminder, a negative delta G means that the reaction is spontaneous. A positive delta G means the reaction is not spontaneous. And a delta G that is equal to 0 means the reaction is at equilibrium. Here we see that the more negative the free energy, the further the reaction will go to the right to reach equilibrium. So in other words, if your delta G is -5, then the reaction definitely favors products. But if your delta G is -50, then the reaction favors products even to a greater extent. There'll be even fewer reactants left at the end of the reaction. It will virtually go totally to products. And that trend continues. The more negative the delta G becomes, you'll see fewer and fewer molecules of reactants existing because they have converted into products. We must use standard state conditions because free energy varies with pressure and concentration. So all of the methods shown above are for standard state conditions. These are some reminders of how temperature can play a role in free energy depending on the value of entropy and enthalpy. You may recall that if enthalpy is positive or the reaction is becoming more random and delta H is negative, which means the reaction is also exothermic, then that reaction is definitely spontaneous, regardless of its temperature. And if you think about it, any chemical reaction that's giving off heat and becoming more random, those are very good signs that it's happening without any prompting. Here, we're reminded that when the reaction is becoming more random but is requiring heat to occur, then high temperatures are needed. Thirdly, when the reaction is becoming more orderly and giving off heat, then low temperatures are required. And if it's becoming more orderly or losing entropy and it requires heat, then the process is never spontaneous. It's like this is getting very orderly and energy is being put in to make it occur. That's not spontaneous at all.